In this video, we're going to discuss lattice energy. What is lattice energy? Lattice energy is the energy involved in bringing the ions together. It is the energy of the attraction of the ions to each other. If we think about sodium chloride, well, that is really Na plus and Cl minus pulled up next to each other. So a positive and a negative adjacent. Well, if they originally were apart, they would have more potential energy. They'd drift through space, and as they got near, they'd pull in. They'd suddenly start moving as they got attracted, and they'd convert some potential into kinetic. And then when they met each other, it'd cause vibrations and become heat. But they have potential to be attracted to each other. That potential is what we're looking at here. Because if we think about making these compounds, if I have sodium and I go to sodium plus and an electron, well, the ionization energy to do this, the delta H of the reaction, the first ionization for sodium was 500 kilojoules per mole. It's really about 495, but I'm going with what our book has. And if we think about the chlorine, if I want to take that electron and move it onto a chlorine atom and make chloride, well, that's the first electron affinity. Chlorine's electron affinity is negative 349 kilojoules per mole. This means if I just throw sodium and chlorine together, I have to put in 500 kilojoules and I get 350 back. So I'm out 150 kilojoules per mole. This would be endothermic at the moment. But if you actually drop a piece of sodium into a beaker with chlorine gas, it lights up like the sun. These are very exothermic. So what's really happening is, well, initially, these atoms aren't near each other. I have a sodium, I have a chlorine, and there's an electron over here. That electron moves, makes this a minus and a plus, and then these come together. Our equation hasn't involved that part yet. But you can't have ions really be free on their own, so they're going to pull towards each other. How do we determine that energy? Well, Hess law. We can cheat with Hess's law. Actually having free-floating sodium plus and free-floating Cl minus and watching them come together is effectively impossible. We can't do it. But we can imagine a set of reactions. I want sodium chloride solid. I want to find the energy, the lattice energy, which is our sodium ion free-floating, not attached to anything, so a gas, and a chloride anion free-floating, not attached to anything, gas, coming together. This removes all the other complicating anythings. I have just the free-floating ions come together to make the solid. That is going to show me the attractive force between them. How strongly do they pull together to hold into a lattice, a crystal? Well, how on earth would I get there? Because normally what we do is we have sodium solid and we have Cl2 gas. Now, if we just throw these two together, we see it give off energy. Like I said, it lights up like the sun. So, our energy's on the side here. They have to give off energy, but our affinities and our ionization energies don't support that. Well, this is because there's another route. We can go up. Let's turn that sodium into a gas. So first thing first, let's make it all gas. So boil sodium. I have to put in some energy to make it sodium gas, but now it's the same state as I want it to find that lattice energy. And I still have my chlorine, nothing happened there. Cl2 gas is hanging out. But I don't want Cl2 gas, I need Cl gas. And so there's another energy. I've got to put in a little bit of energy here to break this into just chlorine free-floating atom, which means I don't really want two of them. I needed a half Cl2, I needed a half Cl2, and that'll break into a full mole of just chlorine gas. My sodium is still here, it didn't change. And so all I did here was break Cl-Cl bond. I broke them into free-floating atoms. Well, we're closer. I've got gaseous states now for both of them. And I can keep putting in energy. It's like, oh, okay, what's the next energy? Let's turn that sodium into sodium plus. So sodium's ionization energy. I could put some energy in, make it sodium plus as a gas. My chlorine is still hanging out here. Next step would be to react it so that I can turn my chlorine into chloride. Well, that's actually going to go down in energy. That's favorable. And so to get Cl minus gas, which means we're going to want to adjust this a little bit. I'm going to go down by the electron affinity. And it will bring the sodium with it. That didn't change, so sodium plus gas. Effectively, I've reached my target. If you actually were to measure throwing sodium solid and chlorine gas together, you could find the energy to go down. So there's a delta H of this reaction. You could find the delta H of vaporization for sodium. You could find the delta H for breaking the chlorine-chlorine bond. You could plug in the sodium ionization energy. You could subtract the electron affinity. What you'll find is you'll have gone up much more than you came down, and the difference must be the attractive force of bringing the ions together. It must be our lattice energy. Now, this is a visual representation. We could do these as Hess laws. Na solid plus 1/2 Cl2 gas going to NaCl solid would have some delta H. So that'd be one reaction. One would be your sodium solid going to sodium gas. It'll have its own delta H. Your chlorine gas breaking apart into chlorine atoms gas with its own delta H. The ionization, our sodium gas going to sodium cation gas plus an electron. Your chlorine gas plus an electron going to chlorine minus gas with its own delta H. And finally, your Na plus gas plus your Cl minus gas going to NaCl solid. And this wouldn't actually be one of our variables. This would be the one we're solving for. This would be our target reaction. You could solve the delta H of that reaction. For ionic compounds, which clearly there are lots of rocks and minerals in the world, these are very favorable compounds. We have to recognize that the ionization alone does not favor making them. In fact, it never favors making them. The highest electron affinity for any of the reactive elements is chlorine at 349 kilojoules per mole. Sodium, one of the most reactive metals, wants 500 kilojoules. Even if you go down to potassium, which wants a little bit less, it's still 480 some. Effectively, the metals that want to give up electrons the most still take more energy to do it than the atom that wants to steal that electron the most. The transfer electron alone does not explain ionic compounds. For that, we have to have lattice energy. The attractive forces of those newly charged ions pulling each other towards one another, spending potential energy to bring themselves together.